Now we start looking at practical exercises with SolveCAD, starting from the very basics. We have prepared a series of exercises that we will share with you in due course. You will find the link. And here is the exercises. So starting from the simplest to the most complicated. We will see only the simpler exercises in this lesson. First exercise asks you to compute water and CO2 solubility from 5 kilobar to the surface for two different melt compositions as expressed here. Okay, so temperature is given, and the pressure needs to vary between 1 bar and 5 kilobars. So let's take a look at how we can solve these problems. Okay, now here I have a shell opening, which is in the folder where I have solved these exercises. So let's start from the first exercise, okay? What we have here, you see that we have the executable that we have seen. We have the two input files, sw.data and swinput.data. And then there's some outputs and figures that I have calculated and that I will show you later. So now, what we're going to do is first edit the input files. Let's start with SW input. You can use any text editor that you want. SW input.data. Now here, what we have here is the rows for SW.data. KL here is set to 1. If you remember, KL if equals to 1 means that, let's open the other file here, sw.data, means that the pressure that we set here is the starting pressure. And then SolveCAD will perform calculations up to ambient pressure. Okay? IOPEN is 0 because there's no gas loss in this case. And the temperature, we don't care. So we can leave these numbers as they are. I have prepared here two lines already. One for the basalt composition. If you see, what I've set here is pressure, the starting pressure that is 5 kilobars. And then the temperature that for the basalt is 150 Celsius, which is 1323 Kelvin. And then total content of water, we want to calculate solubility of water. So we need to put a very high total content of water so that we don't run out of it, because if it's all dissolved, then we cannot calculate solubility anymore, because you can't solve more than what you have in total. CO2 needs to be set to 0. And then there is the composition of the melt, of the silicate melt in the order that is given here, exactly copied from here. So now let's run the calculation for the basalt, okay? We go back to our shell. We are in the right directory, exercise 1. So what we need to do is to run SolveCAD. And to run SolveCAD, the command is // and the executable name. Okay, so it's the output, and it is also saved in the file solvecad.out. Let's take a look at these solvecad.out files that we have been talking about also earlier. And this is the output. You see, pressure is varying from 500 megapascal to 1 bar, atmospheric pressure, temperature is the same, total water, total CO2, and then dissolved water and all the other data that we have seen before. This is for the one. I can show you a figure. With this data that I have prepared earlier. You can use any software that you want to see this figure and to produce it. I have used Nuplot to produce it. And I'm going to use the, GIMP to see it. So this is the solubility curve for the basalt that that was requested. To plot it with the Nuplot, I don't know if you're familiar with that, but it's a very easy software. And basically, what you need to do is to call it from a terminal window. Let's go into the right directory. Where are we? Okay, we're here already. So and then you just type plot the name of the file that you want, and we want to plot first column against fifth columns, that is pressure against dissolved water content. And you see that the graph is exactly what I have just shown you. Okay, so this is on water. If you change fw.data and use the composition of rhyolite instead, put it in the first line for the calculations to be run on this, and run the calculation again. Your solvcut.out will change. Run the calculation again. Plot it again. And you see that it is slightly different, and you can actually see both together here. Not the curves together. Sorry for the white spaces. So rhyolite is the violet and basalt is the green. And you see that water dissolves much better in rhyolite, in basalts, in rhyolites at high pressure than in basalts. For CO2, if we want to run calculations for CO2, we need to change water content here to 0 and CO2 content to a lot, like for example 1%, which is quite a lot for CO2, and then run the calculation again. And then see, plot it again, but now it's not 5 that we want, it's 6, because in solvcut.out, the 6th column is the dissolved CO2 content. And here it is. You see that, of course, the CO2 is much less soluble. It's much more in the fluid phase. So if you look at the CO2 solubilities for both, which is here, you see that the values are much smaller. We're talking on maximum thousands of ppms. And the curves are a bit more complicated. It varies much less for rhyolite, while for basalt at large pressure, CO2 starts to dissolve a bit more efficiently. So this is just to calculate solubility curves. Now let's take a look at saturation. For example, the second exercise asks us, for the basalt that we have seen earlier, explore the saturation curve for the case for a given quantity of water and a given quantity of CO2. So let's first run this exercise that we are asked to run. We change direct to the one that is related to this exercise here. And again, we have some stuff that I prepared earlier. Let's take a look at SW.data. SW input doesn't change because, again, we want to see a saturation curve. So we want to see pressure variations. Let's take a look at SW.data. Okay, so here we have the exercise here. That is 3% of water and 2% of CO2. Here it is 0. If we want it to 0.1%, here it is for the same composition as before. Let's run SolveCAD. And let's plot it. We need to change directory for new plot again and plot the same thing. This is solubility for 0.1% of carbon dioxide. What if we put carbon dioxide to 0? What happens? Let's run SolveCAD again, but let's change name to the output. For example, no CO2. Exercise 2. Sorry, exercise 2. Here we have the saturation, and if we add CO2, here are the curves, and you see that CO2 does change the behavior a little bit, right? What CO2 does, it basically removes water from the liquid and makes it dissolve. So as we increase the CO2 content in a magma, water will go from the liquid phase into the gas phase. And this is also asked to do in exercise 3, exploring the saturation condition, assuming a given amount of water and different amount of CO2. You need to modify SW.data accordingly, but the results that I will show you now are here for exercise 3. Is always the same figure. Water, dissolved water as a function of pressure. And you see that it increases CO2 content, which is the orange line, to the fluid phase. And indeed, what you see for the fluid phase is that the weight fraction of the fluid phase, including both water and CO2 in this case, this is the overall fluid phase, which is also an output from SolveCAD at columns 9 and 10. You see that increasing CO2 dramatically increases the amount of exhaust gas in the overall system. And this is very important in terms, for example, of density, compressibility, and amount of bubbles that a magma can generate. So even a small amount of CO2 can generate a very large amount of fluid as it moves water from the dissolved into the exsolved phases of the fluid. For this session now, these simpler exercises, next step is going to be to show you how to interpret data sets from melting